Production Nicholas está.
Okay, let's get started. It's 4:02 right now. So hello everyone, and welcome to today's workshop on multivariate analysis on R. This is part of the agronomy graduate student stats and programming workshop series. Thank you for taking time and being here today. I'm Carlos Pires, and I'll be the moderator of today's workshop. Dr. Leonardo Bastos, our invited speaker, will cover topics such as principal coordinate analysis, non-metric multidimensional scaling, and k-means. Dr. Leonardo Bastos is a postdoctoral researcher at Dr. Ciampides' lab, and he has a bachelor in agronomy from the Federal University of Santa Maria in Brazil, a master's in agronomy from K-State, and a PhD in soil fertility and precision agriculture from the University of Nebraska-Lincoln. Dr. Bastos, thank you very much for your continued support to AGSA. That's your third workshop with us. And I want to remind everyone that a recorded version of this workshop will be available on the AGSA YouTube page. If you have questions during the workshop, please use the chat button, and Adrian and Logan will help me to direct these questions to Dr. Bastos. With that being said, Leo, the floor is all yours.
Awesome. Hey, everybody. Welcome to the first day of the Multivariate workshop. Thanks to Carlos and all the AGSA people involved in the stats and programming committee to invite me again back this year. So if you're not aware, this is the third year that we've been working with AGSA to provide these types of workshops. And in the past, we've provided workshops related to basics in R programming, and also talking a little bit about experimental design, random and fixed effects, regression versus ANOVA. And this year we focused on multivariate analysis. So today I'm going to be sharing you a couple of analyses that can be used with multivariate data. And tomorrow, Adrian is going to share the second part of this workshop with you. So there's going to be a live coding workshop. And by that, I mean, I sent you the link to download the material that has the partially filled script. And so I left a lot of the more complex coding in the script, but I removed some parts. And that's because I wanted to do those parts with you together. And so, you know, having said that, it means that you really have to have the material that I shared earlier to be able to follow today. And I'm just going to start sharing my screen here because I want to show you my desktop and how I'm going to launch the project. So you downloaded a zip file that should look like this. So 2021 R workshop KSU. So when you please go ahead and open that folder and click on that R project icon there, which has the same name as the folder. And this should, just give me a second here. This should launch your RStudio environment, where you're gonna have all the files within that project that you downloaded. And so this is what you should be seeing now. If you come on Markdown, so this is RStudio if you're not familiar with. I hope you are, because this is an advanced workshop. So you would come, this would be, you come to the Files tab, you would see the files within this project. You would click on your Markdown folder and you would click on your partially filled scripts. And that should open up here. If you want, feel free to minimize your console window by clicking on this button here, because we're not going to be using the console as we're using our Markdown files. And we're going to start here. So let me just check something. All right. Okay, so just some quick notes before we get started. So this workshop is going to run from now all the way to 6 p.m. And it, as Carlos said, it will be recorded and made available later on the AGSA YouTube channel. And also the complete script of this section today will be made available later tonight on the same GitHub page where you where you downloaded the rest of the material. And so this is an advanced workshop and assumes that you already have knowledge about our studio projects, our markdown files, and also some key packages of the tidyverse family like dplyr, ggplot, and how to use the pipe operator. If you're not familiar with these topics, you will likely get lost at some point. And unfortunately, we're not going to have time to troubleshoot those types of problems today. However, because this is being recorded and you're going to have the complete script by the end of today, you will be able to go back to these videos and to the code and follow along at a later time when maybe you have already learned some of the concepts that we assume you know by now. And so some of these topics we have covered in previous workshops, and they are available as well on the AGSA YouTube channel. Please feel free to access that material if you want a refresher on some of these topics that we are assuming that you know already. And so if you have any questions related to the topics of today, feel free to type that in the chat, and Carlos, Logan, or maybe somebody else will help us to answer those. And before we begin, I just want to show you here. So I just want to point a couple of things out before we actually get started. So the first one is, if you're not seeing, so this is a table of content that I have right here showing with my cursor. If you're not seeing that on your script, you just need to toggle this button here on. So this button right there that looks like a table of contents, just toggle that on. That's going to help you to browse the code a little bit better because it is divided in different sections. So if you bring your cursor back to the main part of the file, I'm just going to browse down a little bit because I want to find a chunk. And I want to quickly give you a few tips about chunks. So if you already have all the code for that chunk, which you're going to know just because you're going to see me coding more or not in that chunk. If you already have all the code and you just want to run the whole thing, you can just click on that play button right there. And that play button is going to run that chunk by itself. Carlos, I can hear some noise. Maybe somebody has the.
Let me check that I can mute.
Yeah, if you can check that, please, that'd be great. Thank you. Okay, and so that play button will run the entire chunk, right? But let's say if you just want to run part of the chunk. So let's say I just wanted to run this part here, this theme set function, which you don't really have to know. If you don't know what that is, you don't really have to know much about it, just that we want to run it by itself. I would put my cursor anywhere within these lines of code here. So anywhere here I can place my cursor, and I would press Command and Return. And that would run just this piece of code here. So again, Command Return on a Mac or Control Return on a PC, it's going to let you do that. Okay, so I think those were some of the notes I had for you before we actually took a look at our agenda for today. Okay, so very quickly, today we're going to cover the following topics. We're going to talk about what is and when to use a multivariate analysis. We're going to talk a little bit about some different types of multivariate analysis. We're going to import a soybean yield data set that was provided by Adrian from one of his papers, and that has multiple variables, and we're going to play along with that data set to understand some concepts about multivariate analysis. We're going to talk about multicollinearity, its effects, implications, and how to remedy multicollinearity issues in your analysis. And then I decided to actually cut down a little bit. I was originally going to talk about 3 topics, but I decided to cut down to just principal component analysis, which originally was principal coordinate analysis. I decided to change to PCA for simplicity. which is a dimensionality reduction technique. And then after that, we're going to run k-means, which is a clustering technique for multivariate analysis. Okay, so I don't have any slides. Everything I'm going to tell you and show you are going to be on this script that you're seeing in front of you. And so, I just want to quickly go through some of these concepts here. So what is a multivariate analysis? What defines it? So basically, the most common type of multivariate analysis is when you have multiple x's in your equation or multiple predictors, right? So we have a formula that looks something like this, where you have y equals x1 plus x2 plus any number of predictors. So that is what a multivariate analysis really is. So for example, we could have yield explained by precipitation, temperature, organic matter, hybrid, and so on. Sometimes some multivariate analysis do not only have, they don't have an outcome like a y. They don't really have this part here. They only have the predictors themselves. So it would be something like this. You would not have anything before the tilde, and then after the tilde, you have all of your predictors there. And at the same time, other types of multivariate analysis have multiple y's and multiple x's in the same formula. So this would be a case that is called multivariate ANOVA or MANOVA, where you would have, let's say, yield and biomass as your outcomes explained by any number of covariates that you have measured. So this is basically what a multivariate analysis is, right? And then when do we really use multivariate analysis? So this would be when you have multiple predictors that you want to use to explain an outcome, or perhaps you want to use those predictors to create data-driven groups or clusters, right? And so commonly, if you think about it, these approaches that we're going to be talking today and tomorrow are not really something used with design experiments, in the sense that normally you're not going to have like block and like different structures of experimental and treatment design in a multivariate approach, just because your study has been designed away and you don't really play with the variables that go in or out of the model. Whereas the sense of multivariate that we're going to be showing you today is like you measure a whole bunch of variables that perhaps had nothing to do with your experimental or treatment design, and now just want to see what sticks, right? So that's where we headed today. And then there are some different types of multivariate. As we said, one of the main types is dimensionality reduction, where PCA is one of them, principal component analysis, but there are others in that group. And I'm just listing a few here because there are actually a whole body of literature on different types of multivariate analysis. So besides dimensionality reduction, we have clustering, where k-means is one of the most popular algorithms. We have others here that I'm not going to list, but they're here for you to read if you want to look for them. And also there are some approaches that are just help you to establish a relationship between your variables and to create models for prediction. So for future data that you don't have yet. So multiple linear regression or stepwise regression would be one example. And then of course, random forest and conditional inference tree, which you're going to be seeing tomorrow, also fall within this category. And a few other ways to characterize multivariate analysis that exist. So because multivariate analysis is something that it encompasses so many different analyses that is a little bit difficult to really say, this is how to categorize all of them. So you could categorize different multivariate analysis based on your goal, right? So if you want to decrease the number of dimensions, create clusters, or create a predictive model, that could be one class that you could use to think about multivariate analysis. However, you can also classify them by the existence of an outcome or like a measure variable or response variable. If you do have a response variable that you want to use as part of with the multivariate analysis as the outcome of the analysis, that would be a supervised type of analysis. However, if you don't have that, either you don't have the response variable or you don't want to have that included as a response variable, but actually as a predictor, that would be an unsupervised analysis. And today, both PCA and k-means are unsupervised, and you're going to see why when we get to them. And also, if you are running a supervised analysis, then the type of variable that your outcome is important. If it is a categorical outcome, your multivariate analysis would perform a classification task. Whereas if it is a numerical outcome, it will be a regression type of multivariate analysis. So there are just some different ways of thinking about this. And I just wanted to kind of summarize quickly here for you to understand. Okay, so we got to our first chunk here. Please go ahead and run. You can just run the entire chunk right there. You should see something like this, all packages loaded successfully. If you have not seen something like this, please feel free to type in the chat and maybe one of the guys will be able to help you. I will not be able to stop to help with that, but maybe somebody else would. And here we're just basically installing and or loading our packages that we're going to be using, and then just setting the theme of our ggplots up here. So we don't have to be repeating that for every plot that we make. All right, so the first thing that you're going to help me here is let's read the data set. So I'm going to use this function called read CSV. I'm going to save the data set into this object here. I'm going to call multivariate analysis df, so MVADF. To do that, I want to ask you to place your cursor in between the parentheses, open and close quotation marks, have your cursor blinking in between the quotation marks and hit tab. So right now the tab is showing you the markdown folder, and we have to get outside the markdown folder, go inside the data folder. So to get outside markdown folder, we use .. and hit tab again. If you are on a PC, maybe it is a backward slash instead. You can try that, just a heads up. So hit tab again. Let's use the keyboard here to go to data and hit enter and hit tab again. And then our data set appears. So this is what you should have here. And you can just go ahead and run this piece of code here on the chunk. And it's just going to give you some information about how we could categorize different columns. Okay, so I see we have some. Oh, awesome. Thanks, Carlos, for helping with the packages. Okay, so our next chunk here is really just to print the object that we just saved. So I just want to print it. So, you know, right now I just place my cursor and then push command return to run it, but you can also use the play button there. So this is the data set that we have. It has 600 observations and 41 columns. So these columns we have GY is grain yield, and this is a soybean yield. Till is a tillage type, or if it was tilled, so yes or no. Fungicide has 3 levels. Inoculation has yes or no. And then we have all of our numerical variables. So organic matter, clay, silt, sand, and a whole bunch more that right now I'm not going to go over them, but we have 41 columns, so 41 predictors in this data set. So let's go to the next chunk here and just run it and check the summary of this data set. So the summary function is basically going to tell you that if it is a numerical variable, is going to give you the quartiles and minimum, maximum, mean. And if it is a categorical variable like till, it's just going to tell you the length of that variable. So this is just for us to have some idea of the range of the data. I'm not going to get, oh, just let me point out something else here as well. So PP is precipitation, and then TM is mean temperature. We have TM lower here somewhere. And then let me just go back up. I just want to show you again. So pre 1, 2, 3, and 4 are just pre is before planting, and then 1, 2, 3, 4 are the months after planting. So these would be, so for precipitation, this would be cumulative precipitation during that month. And for temperature would be the mean temperature. Okay, so you can just go past that output, and let's just get closer to the next chunk here. So something I want to do some light data wrangling here. And basically what I'm doing is, first I want to clean the names. So right now the names, I'm just gonna, you don't have to do this right now, but I'm just gonna print again just the data set above, just so you see. So some names are uppercase, others are a mix of upper and lowercase. And I just wanted to standardize that. And to do that, I'm going to use the function clean names. So just clean names basically does that. I'm just going to run this piece of code here just so you know what clean names is doing. It's basically just making all the column names standardized. And then what I want to do is, if you see here, the columns that have numbers are being considered by R as double, or you know that by the DBL, which basically means numerical. And then any variable that had a character in the levels was understood by R as being of class character. And I actually want to change the character ones to factor. And we don't really have to tell much about why I want to do that, but I want to do that. And so here there would be 1, 2, 3 columns that are character. This next function here, this next mutate, basically does that. It looks where there is a character column and transforms that into factor. And then finally, what I wanted to tell you is we do have 41 predictors right now, but I want to reduce that a little bit just to make it easier when we're making some plots. So we're not going to be using all the 41 predictors for the next analysis that we're doing today. Perhaps Adriana is going to use all of them tomorrow. Today, I decided not to use all of them just for simplicity. But I think we're going to get down to 24 predictors, which I think is already complex enough to make the point that we're trying to make with multivariate analysis. So with that, I'm just selecting the columns that go from grain yield through sand. So I'm selecting grain yield till fungicide inoculant all the way to sand. So all these columns. And then anything that starts with PP, which is precipitation, TM, which is mean temperature, RAD, which is radiation, or VPD, which is vapor pressure deficit. I just want to keep those columns. So if I run this piece of code here, and then I print this outcome here, which is the MVADF_W, and W stands for wrangled, you see that now we have 27 columns instead of the 41 original ones. But that's what I wanted to work with today. Okay, so the first thing that we're going to do here, and really something that we should always be doing with any analysis, is doing some exploratory data analysis. And what does that really mean? It's just like taking a look at your data, seeing if it makes sense. You know, like if you have a soil organic matter value of 100, we know that doesn't make sense. So it's just like to check those things, check some errors. And in this case here specifically, because we're doing multivariate analysis, I wanted to explore the complexity or the correlation between all these variables. So please go ahead and just run these functions right there. So I'm creating a matrix of p-values here, and then using that data set that we just wrangled above, selecting only the numerical columns, using the function core to get the correlation, and then using the function EG_core_plot to create a correlation matrix of all these variables. So please just go ahead and run this. We're not going to get into much of the details of what is going on line by line, but I just wanted you to run this. And you're going to see this come up on your below here on your chunk. It is very difficult to see, at least for me, my computer on this chunk. So that's why I saved it to file. So I saved on the output folder. If you come on this side here and you click on that R symbol there, it takes you to the home folder or to the main folder of our project. And if you go to output, you're going to see this core_mat.png that we just created. You can just open it. I'm going to open here. You're going to be able to see on my end, but you also have this file there. So this is basically a correlation matrix. And this is just R, it's not R squared. So that's why we have positive and negative values. So going from -1 to 1, and we have all the variables here. And if we just take a quick look at these variables, we see that the brighter the brighter red values here are higher positive correlation. So for example, 0.9 is the R value between temperature mean 4 months after planting and vapor pressure deficit 4 months after planting. So this is how we would interpret this type of matrix. And anywhere you see a blank is because that correlation was not significant. So this is just to give us a general idea of how well or poorly correlated our predictors are. And this is really important for multivariate analysis, because we're going to see in a second here how having highly correlated predictors in some multivariate analysis can be a big issue when we talk about multicollinearity. So for now, I'm just gonna, let me just check something here before I close that. Let me make sure. Yeah, I'm just gonna close this right now and move to the next chunk. So because grain yield is our main response variable here, even though we're not using grain yield as a response variable in the analysis to come on PCA and k-means, but it would still be our main variable of interest, right? What I wanted to do is basically take all of these variables that we have here and do like a bivariate linear regression against yield. And I'm not doing this statistically per se, because I'm not interested in that, but I'm just doing in a exploratory way to see how strong things are related to yield. So what I'm doing here is taking that original data set, selecting only the numerical variables, reshaping this data set to, and I can just run this up until here so you see what's going on. I'm reshaping this data set. Well, you know what, let me just go 2 lines at a time, or first print the 2 lines here. So taking the data set, using the pipes here, I'm going to be using a lot of the pipes. So just so you know, basically only selecting the numerical columns on the data set. And then I'm reshaping the data set to have all these columns below each other and just in this way. So grain yield is basically repeating itself. And then I have the name of the variable that before was a column and the value that before was a cell. And basically doing a ggplot here where I'm just going to run this, and you're going to maybe easier to see than just to listen to me explaining it. But it's going to make as many plots as there were variables and relate each variable to yield and add a regression line just visually for us to see the strength of the correlation between those variables. And so this, I mean, shouldn't take too long to run, but it's going to basically save the result again on the output folder on that, and it's going to be called grain yield vcell.png, and you can find that. You can find that on the same place where we have the other plot. And I'm just gonna, it's taking a little bit longer, I guess, perhaps because I have Zoom also going on. Let me see if it lets me open this while it is still running. Probably for you, it's not taking this long, but this is the plot I created. So if you, I'm just gonna zoom here just to see a little bit better, because right now, you know, there's a lot of stuff going on. But for every plot, the y-axis is grain yield, and the x-axis is the variable which name is shown on top. So the first plot here would be yield versus clay content, and then yield versus precipitation 1 month after planting, and so on. So all those variables are here. I'm just going to zoom out and ask for you to focus on the yellow lines, which are the regression lines. You know, so we do see that it looks like some of these variables are positively correlated, others are negatively correlated with yield, but nothing really strong, right? We're not seeing any strong correlation of any of these variables with yield, which is, I think it makes sense for this data set here, especially because it is a large geographical scope. But this is just something that it's always good to do, right? Always good to check what your raw data looks like before you really start running any hardcore analysis, just to kind of adjust your expectations and also kind of think about what could come out of this from when you're doing any analysis. So these are the 2 main exploratory data analysis approaches I took with this data set. So first to look at all the correlations between all variables, and then looking at the bivariate correlation between each variable and yield. Okay, so now we come here to the fourth point on multicollinearity on our script. And I just have some more concepts here, and I'll be showing you some graphs as well, so you don't have to just be listening to me, but also seeing some things to connect with these concepts. So basically, multicollinearity, the definition of that is when more than two explanatory variables or predictors in a multiple regression model are highly linearly related. That's it. So let's say let's just take a look here at our correlation matrix that we did before. So if we look at here the 0.9, right? So mean temperature at month 4 and VPD at month 4, if we use both of those variables in the model, they are highly correlated, and that model will suffer from multicollinearity issues because of that. But so why is it a problem in the first place? So every time you have multicollinear variables in your model estimates magnitude and direction they can change for those multicollinear variables when you compare a model that does not have those two multicollinear variables together. And not so meaning that the magnitude of the effect, and also if it is a positive or negative effect, can change just because you have multicollinearity variables. And that by itself is not good, right? Because your effect is changing just because you have two variables are correlated, and that should not happen. And also, not only the estimate changes, but the standard error around that estimate becomes inflated, which directly affects p-values, estimate significance, and statistical power of the analysis. So overall, multicollinearity issues are very serious, very easy to happen, and very easily overlooked. If you don't know that they can happen, you may not even care about them or check for them, which could make your models be highly variable and unreliable, basically, which is not something that we want for our research, right? Okay, so when I was thinking about this concept here, I thought, well, we have a perfect data set to show what this means, really. So let's just do that. Let's just really use this data set to understand multicollinearity and what is happening behind the scenes. So I want to invite you to come to the next chunk here, which is called uncorrelated. And right now your chunk is incomplete, and I'm going to tell you where it is incomplete. So basically, it doesn't have the X or the Y variable that I want to show you on this analysis here. And the main goal, not analysis, but actually plot. And what I wanted to do was to get two uncorrelated variables looking at the correlation matrix that we did before, and just select two. So you could select any two where you see perhaps a blank, which means that there's no correlation. When I was doing this exercise, I selected VPD. I'm just going to come here and type VPD pre, which is the vapor pressure deficit on the month before planting, and radiation _2. So please fill with VPD pre and rad2 on your plot. And then if you run it, we're basically just putting VPD on the X, radiation on the Y, and just asking for a smooth line of a linear regression just to really see if they are uncorrelated. And they really look like uncorrelated, right? You increase VPD pre and radiation doesn't change. And that makes sense, I guess, right? If you think about the climatology variables in that sense. But it's just something for us to visually check and really say, okay, these variables are really uncorrelated. Perfect. So now please go to the next chunk where I wanted to do the exercise of using two correlated variables. And when I looked at the correlation matrix, I decided to choose VPD pre, so the same variables we had before on the x-axis, but on the y-axis, I wanted to have TM pre. And I just want to open that correlation matrix here just to show you where they are. So VPD pre is right here, and TM pre is there. So they have an R value of 0.82. So that's the one that we're sampling right now. And before we sampled VPD pre, and let's see where, and red to VPD pre, and then red 2 would be here. Yeah, so it was a blank cell. Just so you know, like how am I choosing these random variables to show you? It's just I selected some that were either uncorrelated or correlated. So now if we run the VPD pre against mean temperature pre, we see this. We see that they are highly correlated, right? And perhaps if you think about weather variables, it makes sense that when you have a higher mean temperature, you have a larger vapor pressure deficit, which basically means perhaps more water stress in that case. So just wanted to show you here two cases, one of uncorrelated variables, another of correlated variables. And now what I want to do is actually fit these models against yield, right? So here you're going to need to help me again with the code. So you do have the LM_VPD, which is the name of the object that I want to give to the model fit. So we just use the assign symbol, which is that less than dash. And I want to use the function LM for linear model. If you recall, so I want to use VPD to explain grain yield. You can basically just copy and paste this formula right there, which matches the name of the arguments of the column names on our data set. And we just have to say data equals, it's the MVADF_W. Okay, so it should look like this. If you run this line of code, it should work. In my case, I was actually missing, and you probably are as well, because I noticed that there was a typo there. So the pre is pre, not just PR. So this is what it should be. If we just print this, it's a regular, LM summary output, which is not what I really want. What I want to get out of this is just basically extract information about this estimate of VPD pre. That's my goal right now. So to do that, I'm going to use the pipe. I'm going to use the function tidy, which comes from the package broom. If I just run this and then print, you're going to see now that instead of having that funky LM output, now we have a tibble, which is a data frame with intercept, the VPD pre, which is the slope, and then the estimates and the error, p-value, and so on. For now, I just want to ask you to add another pipe there, hit enter, and let's use the filter function, because I just want to keep the VPD pre row. I don't really care for the intercept. So I'm going to copy this intercept here, and I'm going to say filter term, which is that column right there, different than intercept. So this is what it should have. If you run this and then you print that LM_VPD, you see just that first row that represents the VPD pre estimate. And I also want to add a last row here. I want to say mutate, because I want to create a column called mod, and I want to give that the name LM_VPD, just so we are having a column here that really helps us to know what model was this that we ran, because in the end, we're going to be comparing multiple models. So we have to give name to different models to really understand what's going on. Okay, so this is what you should have by this point. I'm going to just leave this hanging a little bit there, just for you to see. I'm going to come down to the next chunk here. So the next chunk is this exactly same thing as we just did above. The difference is that we have a different object name. And instead of regressing grain yield versus VPD pre, now we're regressing grain yield against mean temperature pre. That's the only difference, right? And you don't have to type anything on this second example here. You can just go ahead and run that. And then here's the output that you're going to get. Just going to get the same thing, just a different model name, and also different model term, because now it's TM, it's mean temperature instead of VPD, and also estimate. Okay, so what have we just done? If we just stop to think about it, we just ran a bivariate model where first we regressed VPD against grain yield, and then the second one, we regress mean temperature against grain yield. So what happens now if we combine two variables that are uncorrelated into the same model predicting grain yield? So this is what we're going to do in the next chunk below. So if you just come here, you're going to need to help me in this chunk as well. So we're going to use the assign again, LM function, grain yield explained by, and you can actually just copy this formula on the chunk name that's going to match. Then add a comma, we need to say what is the data set name. So data equals that MVADF underscore W. And then we're going to do the same thing as far as adding a pipe, asking for the function tidy, which we just did above 2 times. Add another pipe, filter again, term different than intercept. If you just want to copy the both, the filter and the mutate from above, feel free. But if you do that, just make sure to rename this to LM underscore, I want to call it 2var.uncore. Just make sure you make this change here, and then go ahead and run it. We can print it just to see. So now, because this model has 2 predictors, VPD pre and rad2, now we have 2 terms except like beyond. So we had 3 terms actually, the intercept and then VPD and rad, but we are removing the intercept because I don't really care about it right now. So we should end up with these 2 terms here. And then lastly, the last model that we're fitting here is grain yield, which you already have, so you don't have to fill anything, just run it. Grain yield explained by VPD plus TM. Now remember, when we looked above, VPD and TM were highly correlated, whereas VPD and radiation were not, right? So this is the goal here, is just to now run them by themselves, VPD by itself against grain yield, mean temperature by itself against grain yield, and then run them together in against grain yield and see, just so we can see what's going to happen with the estimates, magnitude, sign or direction, and standard error as well, just so we can really check if those theoretical explanation of multicollinearity actually is happening in our data set, right? So if you haven't done yet, please just go ahead and run this chunk. And now I left all the code here. I'm not going to walk you through what the code is doing. If you're interested, you can check this yourself later. I just want to ask you to go ahead and run this code. So basically, we just combined the results of all those models and now I'm just plotting here. I have 2 plots. So one is for mean temperature pre, the other is for VPD pre. If we look here on the x-axis, we have the different models we fit. So the first one was VPD against grain yield, then TM against grain yield, then the 2 variables together uncorrelated, which was VPD and radiation, and then the 2 correlated variables, which were TM and VPD, right? So what I wanted you to notice here, so if we just look at TM pre first, right? The point here is the estimate coming from those models. So the first model gave a negative estimate. So the model where mean temperature was by itself, right? It had a negative relationship with yield, so a negative estimate. However, when we included TM in the model with VPD, which is the LM2var correlated, and they are correlated variables, we see that the VPD estimate actually changed magnitude. Now, changed direction. Now, instead of being negative, it's positive. And if you look at the standard error around that estimate is larger for when we have the 2 correlated variables in the model. And this is kind of crazy, right? Because the effect of temperature on yield should be the same, regardless if you have temperature by itself or temperature with VPD. This is what multicollinearity is doing, is having this effect. So now if we look at VPD pre itself here on the second plot, we also see something similar, where when VPD was regressed against yield by itself, it had, so the estimate was, all the estimates are negative here, but the standard error was small. And then when we included VPD and radiation, which, so two variables against brain yield, but they were uncorrelated, we see that it didn't really affect that much the VPD estimate and error. It's still very similar to when we regress VPD by itself. However, when we had a model with VPD and mean temperature, which are correlated, we see that there is a drastic change on the estimate of the VPD effect, and the standard error is larger as well. So this is basically all this exercise that we did right now was just to really illustrate what is multicollinearity and how it is impacting the models, right? So affecting the estimate magnitude, direction, and significance by affecting the standard error of that estimate. So bottom line is we want to make sure we don't have multicollinearity issues in our data sets when we do run multivariate analysis. Okay, I think, I'm not planning to take a break, but I just want to maybe open for a second here to see if anyone has any questions about anything up until this point. I'm just gonna give like 1 quick minute to see if something comes up. Okay, nothing came up, just gonna move on. Okay, so these are just visual ways of assessing multicollinearity, right? But now let's think about our case. We have like 27 predictors in our model. We cannot run all the possible models that we just did here with these two variables to understand what is having a multicollinearity effect in our model, right? That would be way too complex. So one way that we can do quickly to assess if there is multicollinearity problems in our data, and then to understand what is causing it, is to look at the variable inflation factor, VIF. So here, so this function here is basically, the argument is just a model fit, and I just basically copied and pasted here the model that we had above. So first one, the uncorrelated model, where we had VPD and radiation against brain yield. So if we just run this function, we get two values, and they're both very close to 1. And a general rule of thumb is that VPD ranges from 1 to positive infinite. The closer it is to 1, it means your variables are not presenting multicollinearity issues. If it is between 1 and 5, it means you have moderate multicollinearity issues in your model, and you may want to take a look at it and fix it. And if it is above 5, you have severe issues of multicollinearity, and you should really, really address them before making any inference with this model, right? So I just want to come back here and show you again the uncorrelated model. If we run that, the VIF values are very close to 1. And the correlated model, where we had VPD and mean temperature, which are highly correlated, had a VIF, so a variance inflation factor of 3. So it would be in that moderate class of multicollinearity, but we still saw above on the plots that we made, analysis that we made, that even that VIF of 3 being moderate still had some very serious effect on the estimates of those models when compared to a model that did not have multicollinearity issues. Okay, so I hope that this was convincing enough to really address what is multicollinearity, how bad of an issue it could be for any model that when we're doing multivariate analysis, and how we can find it, right? How we can identify it. But now, so what, right? Okay, so you do run your model with, I don't know how many predictors, and you know that some of them are correlated. What do you do then, right? How do you fix multicollinearity? So there are a couple of different ways, at least that I could think of from the experience I have in analyzing my own data. There are a few different things that can handle that. So one of them is using an analytical approach that performs dimensionality reduction. And what do I mean by dimensionality reduction? So if you have 27 variables, you have 27 dimensions, right? And we really, if we want to help to decrease multicollinearity, maybe we can go to that correlation matrix, see which variables are highly correlated, which predictors are highly correlated, and just by hand choose one of them, right? So let's say if we know VPD and TM are highly correlated, maybe let's just remove TM from the regression and just keep VPD. So that would be the by hand dimensionality reduction, which can work, and especially if you have strong scientific expertise to say, well, I know that for this response variable, let's say yield, I know that VPD is more important than temperature. I don't know, maybe it is not. This is just an example, right? But that's when you could reduce the dimensions of our data set by hand. Another way of doing that is by using math, right? So that's basically what PCA does, and we're going to talk a little bit more how it does in a second here. But it can also use statistical algorithms to perform dimensionality reduction for you. Other ways of handling multicollinearity that some algorithms already have embedded in them. One is doing variable selection. So instead of you doing your variable selection by hand, the algorithm would actually select some variables at some points of the analysis. Or perhaps a multivariate analysis that is multivariate overall, but is made up of a whole bunch of bivariate analysis, where then you don't have the multicollinearity issue to begin with. And it would be an example of conditional inference tree would be an example of that, which is a multivariate analysis, but it performs bivariate relationships at each one of the steps. Okay, so getting towards the PCA now, I just wanted to make clear that many multivariate, not all of them, but many multivariate analysis, they deal with some sort of similarity or dissimilarity measure among the predictors. And in those cases, especially because you're basically calculating the distance between multiple variables and multiple observations at the same time, if you have predictors with vastly different scales, so for example, I mean, this is not like an extreme example actually, but it is a good example nonetheless. For example, if you have soil organic matter in your model, which ranges, let's say, from 0 to 7%, and then you have precipitation, which ranges from 0 to 300, you have 3 levels of magnitude difference here between these two variables. If you just use those variables as is, the model will tend to give more importance to variables that have a larger scale or a larger range of values. And maybe this is what you want, but normally it's not. Normally, we don't want to allow the magnitude of the variable to have a direct effect on the multivariate analysis, right? And so because of that, we really need to normalize these variables so that the scale of the variable does not directly impact the analysis, but just the importance of it. And so all of our numerical variables need to be normalized. And when I say normalized, I mean, this can mean different things for different people, but what I'm referring to by normalizing here is just center and scale. So center would be removing or doing like the mean minus each value. So let's say you get the mean for all this organic matter observations and reduce that mean from each one of the values. And then scale would be dividing that standard value by the standard deviation of all that column. So that's kind of what I mean by this. And while some analysis do this normalization step for you, like PCA below, others do not. Like the k-means algorithm that I'll be showing you does not do that for you. So you need to be aware of which ones do, which ones don't, so you can do that yourself when the algorithm is not doing for you, because this is an important thing. Again, if the algorithm is not normalizing variables for you and you don't do that yourself, you will be allowing that variables with higher magnitude to be weighed more heavily into the results compared to others that have smaller scale, and that's not something we want to do. Okay, so since both PCA and k-means only take numerical variables, so we're not going to be able to use categorical variables here with these analysis. Let's just create an object that selects only only numerical variables here. So I left you there with the name of the object, which is the MVADF_WN, and the N is for numerical. Sorry if these object names are getting more obscure as time goes on, but it's just a shorter way to really give names. So we're going to use the assignment symbol there, and I'm going to call our original data set wrangled, which is the MVADF_W, and then use the pipe, hit enter, and we're going to use the select function. And this is going to be something important to let you know is select the function. A function called select can come from multiple packages. And if you've been doing data wrangling with tidyverse for long enough, you'll probably ran into the issue of running a select function that doesn't work. And then you spend 4 hours trying to figure out why, and you realize it's because you thought you were using select from dplyr, but it was actually coming from raster package. And that's why it's not working. So just to avoid that issue, I'm going to explicitly call here the package name, which is dplyr, use the : symbol there, and then call a function select. And this, again, is just to force the select function to come from the dplyr package. And then what I want to do, my goal here, if we look again at this data set that we're starting the pipe with, we have some factor variables there. I actually want to remove them, or not remove them, but I want to keep only the numerical ones. So to do that, I come back to the select, and I'm going to use another function called where, open parentheses, say is.numeric without it. So, and stop there. Don't add the parentheses, open and close parentheses, just leave as that. Move your cursor outside. You just want to have just like that. So that is basically selecting all columns are numeric, but I don't want to select grain yield. I want to, and to do that, to say that I don't want grain yield only is you just do a -GY. So that way it's basically selecting all numerical variables except grain yield, because I wanted to keep grain yield outside just so it wouldn't affect the results, and we can actually use grain yield variable later to validate the analysis. Okay, so if you just run that, and you just print the data set that we just created, you're going to see that we have 23 columns of predictors, and they are all numerical. If you just go to the side here, you're going to see they're all numerical. That's what I wanted to do. Okay, so finally, after almost 1 hour of talking, we're finally going to get to do some multivariate analysis, more exciting than just what we were doing up there. So let's get into, yes.
Here's a question from the chat, and I guess about the parameters. So what about ordinal parameters for PCA? It's a question that came from Yamani, if I'm that.
Yes, awesome. Awesome. Thanks, Carlos, for bringing that up. So that's a great question, and it's actually, so PCA and k-means do not handle categorical variables or nominal variables. I like to call them categorical, but they do not handle that. You have to remove them before you run the model. If we actually did not do this step here to remove the categorical variables, and we actually ran PCA with this data set here, which has categorical variables, it would give an error. It would say cannot run because you have categorical variables. And originally, I wanted to show you principal coordinate analysis. And one of the differences between principal coordinate and principal component analysis is that coordinate analysis does take categorical predictors. The thing is, I decided to shift away from coordinate analysis for this workshop just because I was not being able to really find good packages to do some of the things that we're doing here. So I have to do a lot more programming myself, which would make the complexity of the of the workshop even higher. So I didn't want to introduce that, but that's a great question. PCA does not handle categorical variables. They have to be numerical, mostly because it is computing Euclidean distance, which is a distance kind of the sense that we think of distance, right? Like a meter, for example. Whereas if you do have a categorical variable, you cannot compute Euclidean distance. It has to be a different distance metric, which principal coordinate analysis allows you to calculate and use, and PCA does not work with any other distance except Euclidean distance. So that's kind of the answer to that. Thanks for the question. It was really great. Okay, so if you just come down to the PCA part here, I just wanted to tell you a little bit about PCA. So PCA is it is a dimensionality reduction approach that accommodates only numerical variables, kind of what we just talked about. And the way, so it is kind of complex to explain to you how it works mathematically or otherwise, because it is like the more variables you have, the more dimensions you have. And we as humans, at least I guess, I can think of a very limited number of dimensions, right? If you start talking about, 2 dimensions would be X and Y, and then 3 you have a Z, but then 4 and more than that, it's really hard for us to wrap our heads around it. But the number of dimensions that PCA can handle is basically the same as the number of variables you give it. So if you give it 100 variables, it has 100 dimensions, right? Difficult for us to really wrap our head around. But it basically tries to find dimensions of data where it increases the variance explained by each one of those dimensions. And it does that by finding linear relationships between the original variables you give it and the variables that it creates. And just a note here is that PCA works really well when you do have correlated variables. If the variables you're given to the PCA algorithm are already very poorly correlated, PCA is not going to really help you much. It does thrive when you give it highly correlated variables, and many of them. So just so you keep that in the back of your head. So, just a few notes here. PCA is used for dimensionality reduction. We're going to see how in a second here. It is unsupervised analysis because you do not tell it the outcome. You just give it a whole bunch of variables that are all at the same level and just say, find me combinations of these variables that increase variance, basically. And excuse me. Since it does not have an outcome, it only takes predictors. So the formula, you're going to see that in a second here, only takes X values. It does not have anything before the tilde. And again, predictors for PCA need to be numerical. So I found this GIF here online that, maybe makes a little bit easier to understand, at least for 2 variables, what PCA is doing. So, think that you have here 2 variables only. So 1 variable on the x-axis, 1 on the y-axis, and look at the blue dots for a moment. So those are your data. That's your data distribution that you're giving PCA. Let's say if you were only given these 2 variables to a PCA algorithm. So what PCA does is, if the first principal component will always be the one that explains the most variance of this cloud of points. In this case, it would basically be, if you thought of linear regression going through these points, which are kind of like that pink line on the beginning and end of the axis there. That would be the first principal component. And so after he finds the first one, which is always the first, is the one that always explains the most variance, then it goes to the second one, which would explain the second highest variance of all components. So the 1 is always the highest, and then as you increase components, you're explaining less and less variance of your data. So this is what principal component is doing, is looking for those axes between your variables to find where it can maximize the variance explained by a given principal component. And so in this example here, it may look very easy, right? So if you think about it here, PC1 would be this direction and PC2 would be this direction. And then 3 and 4 and so on would then explain less and less variance of this data. But now try to imagine, so this here we just have 2 dimensions, right? Now try to imagine having, I mean, even 3, but you know, think about like 24, I think, what we have here is just a level of complexity that our heads we cannot really wrap that around our heads, and PCA mathematically does it. So this is what is going to be happening behind the scenes, basically. It's just finding those coordinates where you're maximizing variance for each one of the components at a time. So let's run it, okay? Let's just run a PCA now and let's take a look at it. So I want to invite you to come here to the PCA model chunk. I have there the object name that I want to save the PCA results to. So I just want to invite you then to type the assign symbol, and then the function we're going to, I mean, there are a few different functions to run PCA in R. I chose to use the prcomp function. So we're going to give this function the name. So I'm going to come up here just to copy this name here. So make sure it is the WN and not just a W. Remember, the WN has only numerical variables. That's what we want. So I just copied that, came below here, pasted inside the dataset name, added a comma, and I mean, it has multiple arguments, but I just want to say here, scale is an argument to tell the function to scale the measurements for you. So as we were talking about above, PCA scales it for you in the process. So this is what you have to do to tell it to scale for you. So we can just run that. And then in the same chunk here, I just want to do a summary of that function. So summary of mod underscore, sorry, a summary of the object of the model fit. So this is what the summary gives us. So we gave it, I think, 24 predictors, but let me just print this here quickly just to see. No, 23 columns, so 23 predictors, and then PCA calculated 23 principal components. And what is showing us here is just how much standard deviation each one of the PCs is explaining. And as you can see, the highest will always be the first PC. And as you increase on the PC number, you decrease how much standard deviation is being explained. And if you look at the proportion of variance explained as well, is the same. It's just that, you know, the highest proportion is the PC1, and as you increase PC, decrease proportion, and so on. So one thing, so what would you really hope that your PCA would be doing is you give PCA highly correlated predictors. Let's say you give it 30 predictors, and then PCA tells you, look, PC1 and 2 explain, let's say, 70% of the variance of our data. So instead of using 30 predictors, which would explain 100%, you can use 2 PCs and explain 70%. That's pretty good, right? I mean, you basically reduced your data from 30 to 2 columns. Of course, it has a caveat that is not explaining 100%. For you to explain 100% of your variance on a PCA analysis, you have to use all of the PCs. So in this case, 23 PCs, which at that point doesn't make sense, because if you're using all PCs, you can just go back and use all variables. It would be the same information, right? The goal here is that PCA is going to find those highly correlated variables and say, look, all these variables here, we can actually combine them into this PC and explain this much more variance by using just one PC instead of all those variables. That's kind of the what's going on behind the scenes and what we wish that PCA would be doing for us if we give it highly correlated variables. Okay, so then how do you, we can either decide to use 1 PC or 2 or 5 or 10 or 23. How do we make sense, right, of really saying, well, okay, I use PCA, I had 23 variables, but I'm going to continue only with 3 PCs. I mean, great, you can do that if you want, but how did you come up with that number, right? So there is a way that we can have some objectivity to that choice, and that is called a scree plot. So we're going to use a function now from the Facto extra package, which is fvis, so fvis underscore eig for eigenvalue. And then we're just going to give it the mod underscore PCA object, mod underscore PCA. And we could run like this, but I just want to add another argument, which is the add labels equals true. So if you run this, you're going to see this plot, which is commonly called a scree plot, which is just showing us for each PC, what is the percentage of the variance explained for each one of those PCs. So we see, and here's just showing from 1 through 10, just for simplicity, but there's actually 23, right? So we see the first PC explains like 27%, the second 14, the third 9%, and this only decreases as the PCs increase. So one rule of thumb that people use would be, well, I want to explain a given percentage of the variance of my data. If I can explain 60% or 70% or 90% of the variance of my data, I'm just gonna use how many PCs that is, and just based on how much variance I want to explain. So here, if we were to select just 2 PCs, which is very common, right? Because it is like just X and Y, is easy to think about 2 PCs because 2 dimensions. We would only be explaining about 41% of total variance of this data set. Is that good? Is that bad? I guess depends on your judgment. I think that's not good enough because you're still leaving, 59% of the variance outside of whatever you're going to be doing next, which is a lot of variance. So let's say if we thought, I do want to explain 60% of the variance, how many PCs would I need to do that? So I just have some code here that is going to help us to look at that plot. I'm not going to walk you through the code. If you want to, you can come back to this later and run yourself. I'm just going to run it. But basically what this is doing is it's using the number of the PC on the x-axis and the cumulative variance as a percentage on the y-axis. And we see here, and the horizontal line is at 60%. So if we wanted to explain 60%, we would have to select at least 5 PCs for this data set. If the variables that we gave the PCA algorithm were more highly correlated, maybe we would only need 2 PCs to explain 60% of the variance. So this is something that changes from data set to data set. And it has a relationship of how, you're going to explain more variance with fewer PCs, the more correlated your original predictors are. So in our case, we need 5 PCs to explain 60% of the variance. Normally we would wish to select between 2 and 3 PCs, but 5 PCs is definitely better than having 24 original variables, right? We already decreased our dimensionality from 24 to 5. So that's already a gain. Okay, so so I was telling you that each principal component is a linear combination of the original variables. So each component from 1 to 23 has all 23 variables in them. It's just doing linear combinations. Let's inspect the first PC. So here, again, I'm not going to walk you through the code. You can go through this slowly at your own pace later. But what we're doing here is basically, so we have PC1 loadings. So the loadings of PC1 are how important a given variable is weighing into that PC. So on the x-axis, we have all the 23 variables. And then we see that some variables are positively correlated with PC1. So for example, soil organic matter is positively correlated with PC1, whereas VPD, TM are all negatively correlated and I mean, I guess correlated is not the best word to describe, but maybe we can just use that for now just to think about it. But we see that some variables go in the positive direction, some variables go into the negative direction. And we could do this assessment for each one of the 23 PCs. Of course, the first one is the most important because it is the one that explains the most variance. So we can see here that PC1 would basically be a contrast between soil organic matter, sand, and clay versus VPD and TM at different moments. That's kind of the interpretation. And with PC, depending on what you want to do with it, one of the key aspects would be to try to interpret your PCs, right? And this could be very, very difficult depending on what variables you give it, right? I mean, maybe you can say that PC1 here, you know, it is a contrast between soil parameters, some soil parameters and VPD and temperature. So maybe soil parameters versus water stress could be an interpretation. I don't know, something that you can definitely think about if you want to. But interpreting the PCs and how variables are contributing to those PCs is an important aspect. Okay, so now I want to invite you to come to the next chunk here. And we're gonna, so, you know, here we kind of see which variables contributed in one direction and which variables contributed in the opposite direction. So what if we just want to know variable importance of that PC, right? So let's use a function called fvis_contrib or contribution. This is coming from the Factio extra package again. We give the model object name, so mod_PCA. And then it has an argument called choice. I want you to say choice equals var. And then we're going to tell it what PC we want to know about by using the argument axis. So axis equals 1 for the first PC. So if we run this, we get then this plot, which is you can kind of think of this plot as this, but on an absolute scale. So not going from -1 to 1, but going from 0 to 1. This is basically what this here is doing. So it's saying that VPD2, TM2, VPD1, TM1, VPD pre, TM pre are the most important variables. And if we look at the previous plot, we see all those variables right there. And then you would ask, well, but what about organic matter and sand? They were also important. I mean, yeah, they were, but their magnitude of importance was less than these ones here. So if we look for organic matter and sand on the bottom plot here, they're going to be right here. So we see that overall, PC1 was mostly driven by VPD and TM at different moments. So, and then just, you know, wanted to highlight this again. You can do what we just did for all the components and really understand what variables are being more heavily weighted into each one of the components that you use for your analysis after the PCA. So this is just how you would go about it. Okay, so if we come to the next chunk here, I wanna plot the eigenvectors for both PC1 and PC2. And this is probably a plot that you have seen in papers when people run PCA. So what is this, right? So if you think about it, on the x-axis, we have PC1, and it's saying that PC1 explained 27.4% of the variance, as we already knew. And PC2 is on the y-axis explaining 14% of the variance, which we already knew. And now it has added these vectors here, the eigenvectors, on this two-dimensional space to tell us which variables contributed more to each PC. And so one interpretation of this, let's say one of the interpretation is the longer the arrow is, the higher importance it had for that PC, right? So if we look here, the longest that I can see on the x-axis, so on this axis, the longest one is VPD, some VPD, right? VPD2 perhaps, I'm not sure, because they're kind of overlapping. But we knew that variable was already important for principal component 1. So what this plot is actually bringing us is the capacity of looking at two PCs together and how variables are driving each one of those two PCs, but together, right? And another interpretation here is normally variables that are like opposite to each other on a level line. I don't know if that's the best description, but would be negatively correlated. So for example, TM4 would be negative correlated with precipitation 3 because they're kind of in this parallel line here. So that's another way of looking at this plot and how to interpret it. Okay, so another plot that we normally see for PCA is with the PC scores. So this up here is the eigenvectors of the PCs 1 and 2. And now I wanna take a look at the PC scores. So for that, we can use the function fvis underscore PCA underscore end for individual, and then you just tell it mod underscore PCA. So this is what you guys would be trying to type. So in data sets where you have highly correlated variables, you may see clear groupings when you make this plot, like groupings of points, right? You would see like a cluster on the top left, a cluster at the bottom right, and you say, great, I have clusters, right? However, PCA is not really, it's not the best algorithm to create clusters. We're gonna do that with k-means in a second here, even though people still use PCA for that purpose. But just looking at this cloud of points, I don't really see anything that stands out between PCA 1 and 2, right? It's just a cloud of points to me. So something that we can do is still using that same function as above, but we can color things by a categorical variable. So now, even though, so this is important to realize, we did not give categorical variables to PCA in the beginning, and we're not giving it now either to PCA itself. We're just basically using the PCA scores, which are each one of those points, and each one of those points represents one observation of our data set. And we're just matching those scores with whatever categorical columns we had before we even ran PCA. So in this case here, I'm just asking to color those scores by the fungicide variable and add ellipsis to it. I'm just going to run it, and you're going to see what it gives us. So it basically took the observations that belong to each one of those fungicide treatments that we have here on the right. So NF, X1, and X2. So no fungicide, 1 time rate, 2 times rate. And we have 3 groups here for sure that are, that we are imposing our treatment groups, but they're not really distinct, right? Especially the red and the green one are almost completely overlapping, and the blue one is a little bit different, but still completely overlapping with the others. So, what did we really learn here is that, and this happens in our case because the variables that we gave the PCA algorithm were not super strongly correlated to begin with. And you can kind of go back to that correlation matrix in the beginning, and you're going to realize that like the correlations are not really strong. And also because of that, we needed to have at least 5 PCs to cover 60% of the variance of the original variables. That is definitely more than what we wish we would have had, right? And when we look at PC1, the most important variables were related to VPD and temperature. So I guess somebody has a question. I can stop here for a second.
Leo, and I guess a good question. Andrea asked it. Opposed vectors mean negative correlated or weakly correlated?
Negatively correlated, yes. So the strength of the correlation would be more related to the length of the arrow than them being opposite.
A good example would be pH and aluminum in the soil for that.
Yeah, I mean, we don't have that here, right?
Yeah. I'm just, as an example, that will be negative correlated.
Yeah, even though, so, and that's also a good point, because like, to me, if I see a plot like this, I would never use this plot to make the points that TM4 is negatively correlated with precipitation. This is not the plot that makes that point, right? If I want to make that point, I make a linear regression of temperature versus precipitation and show that plot. So this is one of the interpretations that we can get from a PCA analysis, but it's not the main point of the plot, right? It's more just to see how variables are behaving in those two dimensions, which those two dimensions do represent the combination of all variables that you gave the analysis, right? And also something else to keep in mind, again, is for our analysis, these two PCs only explain 41% of the variance. So if I want to make the point that temperature is correlated with precipitation, I want to have all the variance that I have in my data to show that, right? I don't want to use this plot to show, but that's kind of the interpretation, is if they are going in opposite directions, like almost perpendicularly, they are negatively correlated with each other as far as those PCs work. Thanks, Andre. Okay, so finally, we're getting to the end of PC, and I think K-mean is going to be faster. But just to give you an idea, so let's say I have this data set here. Let's say Adrian, I don't think Adrian took this approach on his paper, but let's say that on his paper, he wanted to use PCA to do dimensionality reduction. But why? I mean, why do you do that, right? I mean, so PCA itself, actually, I think I didn't stress this enough. It does decrease dimension, which is a good thing, but the PCs are all orthogonal to each other, meaning PCs are uncorrelated. All PCs are uncorrelated among themselves. So even if you decided to use 23 PCs in a multivariate analysis, they would all be uncorrelated, very differently from using 23 original variables, which some would be correlated and you would have multicollinearity issues. So what if if I were in Adrian's shoes, had this data set, wanted to run PC to decrease dimensionality because I wanted to use all those variables to explain grain yield? Okay, I did PC. I found out that I need 5 PCs to explain 60% of my variance. So what? What do we do next? What do we do about that, right? And this is not something that many papers actually do. And I think it's actually maybe some, I mean, of course, it depends on the objective, right? But I think that if you take your PC results to the next level, is to really use them in analysis to explain something after you came up with them. So that's what we want to do next year. So what I want to do is extract the PC scores of the first 5 PCs and combine those columns with our original data set where we have grain yield, and then do a regression of grain yield versus the 5 first PCs. So to do that, I want to invite you to come to the next chunk, and please type with me here. So when I use the assign symbol, when I call our mod_PCA object, call the $sign and X. So if we look at this, the mod PCA $X is where we have our PC scores. So this would be kind of like each observation would have a value of PC1. Like the first observation for PC1 would be 0.22, for PC2. And I guess you get it. Like the number of rows here is the same number of observations in the data set. Number of columns is the same number of PCs in the analysis. So these are the PC scores. And this right now that you're looking at it, it is a matrix. I want to transform that to a data frame. So if we just do this, I just ran that piece of code and just printing it, this is what we end up with. and I want to only select PCs 1 through 5. So I'm going to use the dplyr : select function, and I want to say PC1 and then colon again PC5. This is basically saying to select from 1 through 5. So if we run this and we print it, we end up with a data set that has 600 observations, 5 columns, where each column is a PC 1 through 5. Each observation is the PC score for each one of our original observations in the original data set. Okay, so now if we come to the next chunk here, you're also going to need to help me here. We're going to create an object where we add those 5 PCs to the original data set. So use the get sign again. Our original data set was called MVADF_W. Just going to print it here just for you to see that. So our original data set, 600 observations, 27 columns. And now we're going to bind columns. So pipe uses the function bind_calls actually. And we're going to call now the name of the object that we created above here, which was PCA_scores. Okay, so if I'm going to print it, you don't have to. I just want to show you what happened now. This new object, it has still 600 observations, but now has 32 columns because towards the end of it, now we have the PCs 1 through 5 scores. Okay, so now in the same chunk, please come down to the LM_PCA, use the get sign. We're going to run a linear model where we're going to have GY, so grain yield, explained by PC1, plus PC2, plus PC3, plus PC4, plus PC5. And then I'm just going to say data equals that we just created up there. So if you run it, and then let's get the summary of this model fit. So I'm going to leave here for you to see. Well, let me stop here actually. So if you want to follow along with the model, you can catch up. And if you're already done there, you can look at the model summary here. So we see that when we are trying to use the PCs to explain grain yield, PC1 was highly significant and PC4 was highly significant. Well, and PC3 as well, sorry. So 1, 3, and 4 were highly significant, but 2 and 5 were not. And then if we, so if you look at this, we just ran a multivariate analysis, right? This has 5 variables as the predictors. And before, I don't know if you remember, but when we ran with VPD and mean temperature, that we had 2 variables, and we checked the VIF, it was 3 when it was VPD and TM because they were correlated, right? So now let's check what's going to happen with the variance inflation factor of this model here, where we use the PCs instead of the variables. Look at that. That's crazy, right? I mean, it's not crazy, I guess, because it is what it should be, but it's crazy to be able to really see that, is that the VIF of all those PCs is 1. And remember, the VIF ranges from 1 to positive infinite, meaning that all these 5 PCs are completely uncorrelated, which is exactly one of the things that PCA does. If we were to include all 23 PCs in this linear regression, they would all have a VIF of 1. So this is, I just showed you here two main goals of PCA. One is to decrease dimensionality. So we went from 24 original variables to 5 PCs. And the other is not only that, but it also, even if you use all 23 PCs, they're all independent, all uncorrelated. And that is a big game changer for PCA. So that's kind of like taking PCA to the next level and really using the PC results to do something else. And of course here, let's say, well, let me just get to the next chunk here, and then I can discuss a little bit more about the implications of this. So let's just plot yield versus PCA1. Okay, so let's call ggplot. So the data frame, you can just come back here and copy and paste because it's kind of a weird long name. That's a data frame. And then we call the astatics function. On the X, I want to have PC1, which is a column in that data frame. On the Y, I want to have grain yield, which is also a column in the data frame. And add a plus, let's add a geom point just to see the distribution of the scatter plot. And then let's add a geom smooth with method equals LM to this plot. Just plot it in. I'm going to leave the code here a little bit longer for you to see if you want to catch up, but this is the result. So we have grain yield on the y-axis, PC1 on the x-axis. We do see that they are positively correlated, but maybe not the strongest correlation. And that's okay because PC, and that probably comes also from the original variables that we gave, were not super highly correlated with yield to begin with, as we did on that second EDA plot. But we can kind of see here that distribution. And then I had a code here for actually the next code should be PC2. You can just basically copy and paste the code you just wrote above and just change PC1 to PC2 and run it as well. Oh, actually, it should be PC3 as well. Sorry, because if you remember from the summary above here, I'm just going to print again. I don't think PC2 was significantly affecting yield. Yeah, PC2 was not, but PC, let's do PC4. PC4 is like a very low p-value. So let's try PC4 here instead. Yeah, I mean, we see there's correlation. There's probably some outliers as well, but so this is kind of, what would be like to take your PCA results to the next level is then use those PCs into a linear regression or perhaps ANOVA, and then trying to use them to explain something else like grain yield in a lower dimensional space than it would be to use all the original variables. So this is kind of one of the goals. Okay, so we finished PCA. I think k-means should be faster. So I'm just gonna stop here for a quick moment to see if anyone has any burning questions about PCA before we move on to k-means. Okay, I think that's enough time. If you have questions, you can still go ahead and post on the chat and I'll take a look at them later. All right, so what is k-means, right? K-means is an algorithm that is going to partition all of the variables that you give it into a number of groups that is called k, and that's why the algorithm is called k-means. However, k is something that you define. You as the user tell it, look, take all this data that I'm giving you, all this soil and weather data, and create 2 groups, or perhaps 3, or perhaps 100. So you are the one defining the number of groups. Of course, we would like to think of it as, we want to have the fewer number of groups that explain the most possible variability. Because let's say, if you have 2 groups, but actually your data set should have 10 groups, then you're not really doing a good job. Your groups are very mixed. However, if your data set, if it should have 2 groups, actually the nature of it should have 2 groups, but you're telling to give 10, then you're really creating groups that are addressing more noise in the data than just the overall trend. And that's also not useful, right? Because we really want to come up with groups that make sense. And I guess one example to think about this is imagine the following scenario. You have a field study and you have 2 treatments, let's say with and without fertilizer, and you are measuring grain yield. And then I go to the field, collect this data, type into the computer for you. So you have all the treatments and grain yield data. But then something happens and accidentally the column where you had the treatment information, so with and without fertilizer, is lost. You don't have that column anymore. And then I say, look, I'm sorry, this experiment was last year. We don't have the field data anymore. We don't have a way to recover which observations came from what group of treatment. You could potentially use k-means to figure that out. You could use k-means and say, find 2 groups here. And hopefully k-means would be able to at least for some of those observations, give you a very good idea if this observation came from a group that was low yielding or high yielding, and then you could assign that to treatment, for example. Of course, this is a very hypothetical example that should really never happen, right? Because you really don't want to lose the treatment information on your Excel files. But it's just kind of to think about it, like you have 2 groups out there, with and without fertilizer. You just don't know what observation is coming from what group, and you want to find that out just using the grain yield data. That's kind of the rationale behind clustering overall, and k-means in this case. Okay, so how does k-means work? So imagine that you have like 2 dimensions. We can actually, I'm just going to print here this GIF just for you to see. So this is not our example. This is an example I got from a blog post. So it's not mine. You can go to that blog post by going to the address before the GIF address there. But this is an example where it has 2. So it has an X variable, Y variable. So just 2 dimensions, and we can clearly see that it has 3 groups, right? So how does k-means work? At the first, it is an iterative process where at the first step, k-means randomly selects let's say if you tell it to look for 3 groups, is going to randomly select 3 observations from a data set and say that those 3 are the center of the groups of the groups that you're looking for. Then is going to calculate the distance from all observations to each one of those 3 centers that you just established, and is going to assign a membership to one of those 3 groups to all observations based on the least distance from the observation to the group center. It does that once, and then it uses all the observations that fell within each one of the groups, recalculates a group center based on that, and repeats the process and keeps doing this until it converges to a state where the center of the group is not changing anymore, which basically means you reach the center of that group. And this is kind of how it is showing. So if we wait until it starts at 0, it goes through 12. So 0, and then you see the steps iterating over, and you see how the group centers are changing, like the X symbols are changing towards the center of each one of those 3 groups. So this is basically how k-means works, and it's very powerful clustering algorithm. So in a nutshell here, k-means is used for clustering. It is an unsupervised analysis because it has no outcome. All the variables are on the right side of the tilde. Only takes numerical predictors. I guess I'm missing here. Only takes predictors, and they have to be numerical as well. Okay, so k-means is highly used, very popular algorithm, but it's not the silver bullet for everything. K-means works very well with circular clusters like this, right? Like we're seeing here. However, it can fail miserably with some other occasions. So I just want to show you here. This is also not for me. This is towards a data science blog post where they're just comparing here. So each data set, all these data sets that we're looking at are fake data sets in the sense that people created those data sets and applied different clustering algorithms to them to see how well they would perform. So the first column here, they call mini batch k-means, but it's basically k-means, right? So let's just first look at this first column of plots. So we see that when we have circular clusters, like in this case, and especially in this case here, k-means did a very good job, right? However, if we look at the first example here, where clearly the clusters are the inner circle is one cluster and the outer circle is another cluster, k-means is split right through them. So it did a poor job in that case because the data was shaped in a way that k-means doesn't really handle well. So in those cases, there are other algorithms that do a better job. So dbScan is one of them. There are others here, but this overall is just to illustrate that different clustering algorithms have different properties, and never one of them will always be the silver bullet, right? There's always pros and cons to each one of them, and it's the same. This is actually the same for any multivariate analysis, actually, right? There's nothing that is the best for every data set. So just for you to keep that in mind. Okay. So k-means does not normalize the data for us like PCA was doing. So we're going to have to do that step ourselves. Let's see here. Yeah, so I left you the code here to do that. So it's basically taking that data set with only numerical variables, which is the same that we enter on the PCA algorithm, and it's just scaling them. So in this case, the scale is taking the mean and dividing by the standard deviation of each one of the variables. And if we just print this now, which is the scaled one, we see, or the normalized one, we see that the values have actually changed for all the variables. Okay, so now that we have our scaled variables for k-means, let's run the k-means algorithm. So the function is called k-means, very intuitive. We're gonna give it the data set that we just created above, so with the normalized data. And as I was telling you, the k-means algorithm needs you to give it how many clusters you want. Okay, so maybe, I don't know, does anybody want to shout out or maybe type out in the chat a number that we can use here just for our initial exploration? Four. Perfect. So we say that by using the argument centers. So we say centers equal 4. And then, as I was telling you, it is something that k-means does is the initial. So let's say we say 4 centers. What k-means is going to do is going to randomly select 4 observations in our data set, and going to use those as the starting points of the iteration process. Because there is a random aspect to this first step, k-means can potentially give you different results on different runs. So to there are different ways to avoid that, but one of the ways that is used is just to use this argument here and start, which is basically saying how many times should the k-means algorithm run to then take an average of the result and give me. So we're telling it to run 10 times and give us the average result of all those 10 times as the final cluster assignment. So we just run it. It runs very quickly. And then if we just print it, the output we get is, so k-means clustering with 4 clusters, and then gives you how many observations fell within each one of the clusters. And then for each one of the variables that we gave the algorithm, here are the center of each one of the clusters for each one of the variables. Great. This is not super easy to interpret, right? You're looking at a whole bunch of numbers and they've been normalized, which makes it even harder to really understand what's going on. So we're going to actually have to play a little bit more with this model here. Okay, so one of the things is we pretty arbitrarily chose 4 centers, right? But there's actually a more objective way to choose the number of clusters. So we're gonna, there's like, I don't know, more than 30 indices you can use to help you select the best number of clusters. There's even a package that can do that for you. Here, I'm not going to use that package. I want to show you 3 indices that are easy to plot and show here because they are within the Facto-Extra package. So the first one is going to be the total error based on the number of clusters. So let's use the function fvis_nbclust. So the first thing you give it is actually, and kind of surprisingly, is not the k-means object fit, but it's the data set that you use on the k-means run. So it would be this one here, the MVA df_WNN. So we give that, and there are a few more arguments that I want to specify here. So one of them is the method argument. So method can take different values. For this one, I want to use the WSS, which is the within sum of squares method. You're going to see what that does in a second here. Add a comma, hit enter, and then there's a k-max argument that basically defines how many number of clusters do you want to explore. So I want to go from 1 to 10. So that's why k-max equals 10. Hit enter. And then it has this argument called fun cluster, which is what function you want to be applied to that data set and those number of clusters to then estimate the total within sum of the squares. And that's k-means. That's basically it. So let's just run it. And what this algorithm is doing is behind the scenes is basically running what we did here once. I mean, we did it here once for 4 clusters. It is doing this for 1 through 10 clusters and just giving us the results. So this is the plot that we get from that. Normally, what happens is you would see more of an elbow shape where it would be more like this. And whenever it tapers off from the bottom, it reaches a plateau, you say, okay, we would select like 4 clusters because the elbow is kind of a 4. Here in our case, by this method and just visually assessing, it looks like 8 or 7 would be the number of clusters that we should select to represent the nature of this data. So this is one of the metrics. We can actually just copy and paste this here. And we're just going to change the method now to gap_stat. So the gap statistics is another index that helps you to identify the number of clusters. I just ran this piece of code here. I'm going to let it run. I think it takes a moment just because it is more math intensive behind the scenes. So it takes a little bit longer. But we can just wait a second here until that goes through. And I'm going to take a sip of water as well. And then, I'm just going to keep talking while it is running. When it finishes running, it's going to show us the plot. And then after that, we're going to run another index, which is the silhouette width, which is also going to give us an advice as far as how many clusters we should choose. So I'm just going to go ahead and copy this, paste here without running, right? If I just paste, I don't interrupt what's running below. I'm going to change the gap stat by S for silhouette width. Okay, so this is the result of the gap stat index, which is recommending us to use 8 clusters as well. So this is the recommendation of the gap statistics. And then if we just come here and run this last piece of code that I just did while the gap stat was running, which I just copied, pasted, and replaced gap stat by S. If you just run that, it's yet another index. And this one actually recommends 2 clusters. So we have, like, visually, if you think about it, from the total within sum of the squares plot, which was the first one, visually seemed like 7 to 8. The gap stat recommended 8. The silhouette one recommended 2. I personally decided to go with 2, just because it's fewer and easier to interpret and to look at. But if you want to, after this ends, if you want to go back to this code and change that to 8 and see how that trickles down to what we do below, feel free to do that as well. Okay, so based on this, I decided to go with 2. And so we can just run this code here, which is basically the same as we did the first time, but now we're seeing 2 centers based on the metrics above. we just print it again. It just gives us the center of the two clusters, and then the assignment of each observation in our data set to be either 1 or 2. That's the membership of the clusters. Okay, so, we have even though we just have 2 clusters, but we have a whole bunch of cluster centers for each one of the variables. I mean, how do we really visualize this, right? How can you make sense? Okay, you have 2 clusters, but how do you see them? How do you know what is what? So there are 2 main ways for us to really inspect how those clusters are affecting the variables, both the variables that went into the k-means algorithm and also variables that did not go into that, like grain yield. As if you remember from the code all the way up on the top, we excluded grain yield from the data set that was used for k-means and PCA. So one of the ways would be to basically plot cluster on the x-axis, so cluster 1 and 2, and then each one of the variables on the y-axis, and have box plots of the distribution of these these variables, just for us to take a look at it. Another way of exploring the results of k-means would be to use a function that summarizes all those original variables into pretty small components and then plot those. So let's do both of them. So here's how the first one looks like. And I'm going to walk you through this a little bit in a second here. And just to let you know, we're almost in the end here. Maybe 5-10 minutes more will be done, just so you know. Okay, so this is the plot. We see we have the cluster. So on the x-axis, we have cluster 1 and 2. And then each one of the panels is one of the variables that we used. And also grain yield, which is, let's see, where is grain yield? Right there, right? So we see now how these different variables behaved across those 2 different clusters. And, if we really wanted, and this is something that I normally do with when I run any clustering algorithm, is not only run these box plots, but actually run those ANOVAs, right? So run the ANOVA like variable explained by cluster. For example, clay, which would be the first analysis here, clay explained by cluster in a LM function, and actually be able to extract the means and comparisons between cluster 1 and 2 for a given variable. So you would be able to actually say, let's say, for example, one here that looks more distinct, perhaps silt. It looks like it is possible that if we ran a statistical analysis, silt was higher in cluster 1 than cluster 2 significantly, perhaps, right? But we only know if we run it, which I didn't here. But that's kind of how you could actually add meaning to those clusters, even though they by themselves don't have meaning. Okay, so the last thing that I have for you is another way of exploring these clusters. So again, the package factoextra has one function that can help us here. So it is called fvis_cluster. And then we give it first the name of the k-means model, which was mod_km2, which was the one with only 2 centers, the one that we selected. And we also give it our original data that went into the k-means algorithm, which I'm just going to go back up here. Let's see. I just want to copy and paste again, which was this one here, and come all the way down here. And check this out. This is super cool. So it's cool, and it may be a little bit confusing at a first glance, right? Because if you first look at it, it's almost like it's the PCA plot. And in fact, it is the PCA plot. So what this function fvis_cluster did, notice that we did not provide the PCA model fit to the fvis_cluster. We just gave the k-means fit, and we gave the data set. So behind the scenes, this function ran PCA, plotted calculated the PCA scores for us. It plotted PCA 1 on the X, PCA2 on the Y, and then it grouped those scores by the cluster coming from k-means. So this is another summarized dimension reduced way of looking at your k-mean results. And it's very clear, right? If we just look at this, it's very, very clear that k-means did a great job separating these two groups between PC1 and 2. And if you remember, I'm gonna go up here. You don't have to, because I don't want you to get lost in your code. Somewhere here, right? It's right here. Look, these are, so this is basically the same PCA, but we're making clusters based on the fungicide effect or the fungicide treatment. Terrible clusters, right? They're all overlapping. I mean, what can you really use here? And also remember that fungicide was not a group that came from an algorithm like k-means. It came from your study, right? It's not something you can really change the group. It is what it is. However, k-means really went into the data and was able to find these very distinct groups that did not exist before. You did not have a column in your original data set that could split the data so well like k-means is giving you here, right? So this is really interesting of how it is happening. Okay, so I know that we are just past the hour, so I'm gonna propose an exercise. I'm not gonna expect you to do now, and even if you don't want to do never, I mean, it's really up to you, right? But if you're curious enough and you would like to see how this final plot would look like if you had 8 clusters instead of 2, which was another recommendation to have, feel free to do this exercise of going back to your code here. So on mod KM2, just change this to 8 and keep running everything below here. And you're gonna get here and you'll be able to see how the 8 clusters are spread into your PCs. So that would be a fun exercise to do. And also just in closing here, a quick summary of what we went through. So we talked about when multivariate analysis can be used, when it should be used. We talked about multicollinearity, how that is a very important issue and a few ways of dealing with that. We went through using PCA for dimensionality reduction, and not only that, but also getting uncorrelated principal components that you can use afterwards in an ANOVA or regression setup. We use k-means to come up with clusters that did not exist originally in the data set, and that k-means was able to find them using the data and the algorithm, of course. And also a few ways of how to validate the results of both PCA and k-means by going back to the original variables, relating the results of those analyses with the original variables, and understanding what is driving really the results of PCA and k-means from the original variables. So this is all I had for you guys. Just, I will open the floor here to any questions if you have. Just before you all leave, I just want to tell you, I will be posting the complete code on the same GitHub repository where you downloaded this. I'll be posting that later tonight, so just so you know. And if you have any questions, let me know. I'll be sticking around for another 5 or 10 minutes to discuss a little. And if you don't have any questions, thanks for attending. I hope you were able to follow along. This was advanced, and so I know that, if you were not able to follow along, don't feel bad. This was really a lot of information very quickly delivered, so that's totally understandable. You're gonna have the video and the record and the code to go back to if you need, and I'm always here to answer any questions if you may have. You have my email address, so feel free to reach out. And now if you have any questions, I'll be glad to answer them.
Hey, Leo, this is Andre.
Hey, Andre.
Man, it was a great presentation, great class, really didactic. Congrats,
Thanks, man.
It was really good. So let me ask you about now the dimensionality reducing using the k-means. So you clusterized it in 2 groups. And then you could potentially run a model predicting grain yield based in group one and in cluster 1 and 2. That would be the next step, the outcome, following up the cluster analysis.
I mean, I get, you could, right? I mean, the way that I've been using any clustering algorithm really is more to, especially when you have so many variables, it's hard, even if you may have some idea of like, oh, I want to take, let's say, precipitation, temperature, take the mean, and then whatever is more than the mean, I'll say is high, like create groups of like high temperature, high precipitation, high temperature, low precipitation, and all the 4 combinations. Even if we think that we have some groupings like that we can force on the data, I think it's always better to use an algorithm to really tell you where the groups are. Because another approach, for example, that we use in our research is to use quantiles to split the data. So you say, I'm going to take 0 from 33rd, it's going to be the low yield, 33rd to 66 medium, and 66 to 100 going to be the high yield. You can do that, but who is to say that those are the correct splits in your data? Maybe your low yield is really like the 10th percentile only. So it's just like using an algorithm to really drive the cluster delineation I think is more powerful to really find those data-driven clusters, And so in my case, when I use k-means or any other clustering algorithm, I'm more looking for those hidden variables, for those hidden groupings that we don't have a column yet describing them. Mm-hmm. And then I use them to explain something else, right? So like yield environment is one that we use a lot in our group. So then you do relate those yield environment. So let's say you do run k-means on yield, for example, which is actually just one variable. So it wouldn't be multivariate, but it still can do that. You come up with different yield levels, yield groups. So you say k equals 3, and then you say whichever cluster is the lowest yield, that's low, that medium and high yield environment. And now you want to understand what is driving those clusters. Then now you can bring other variables, perhaps just like we did here, right? And see, oh, so the yield, I see here that when I have an ANOVA that I have, for example, mean precipitation or cumulative precipitation explained by the clusters, I see that cluster 1, the low yielding cluster was really very low precipitation, like that it followed, right? Like the yield level clusters are following precipitation. So to me, I kind of stopped there, because even though you could use new data and use your k-means algorithm to predict where new data would fall within those clusters, you could do that if you wanted, but I haven't really done that. I more just use other variables to see how they describe the clusters, and I use an ANOVA approach to really have like pairwise comparisons and a statistical analysis of really seeing how those clusters are changing for different variables. I don't know if that really answered your question though.
Okay, so it seems we have a couple questions in the chat, and a great one from Brian, by the way. So since different indices can give quite a bit different optimal number of clusters, would you recommend using multiple indices and see if there is a common recommendation? Any literature you can recommend regarding when to use one index over another? That's a great question.
That is a great question. Yes, thanks, Brian. So I decided to show only 3 here, again, because those are the ones very easily implemented in the facto extra package functions. But there's definitely like many more. In fact, there is a package that is called nbclust. I think that's the name of the package, that it calculates for you, I think it's like near to 30 indices, different indices. And each one of them is different, right? And especially, it depends on your data as well, how variable your data is. But in the end, the output of the function that comes from this package is it gives you like the volts, right? So it calculates the best number of clusters for each one of the, let's say 30 indices. And then each one of them has a vote, right? Each index is telling you choose 1, choose 2, choose 10. And then it shows the output of that package is a plot where it shows you number of clusters voted and the number of votes on the y-axis. So it's very easy for you to see across 30 indices what was the most voted number of clusters to choose. So that is what I actually normally do. But I thought maybe showing some of the, because that, you know, that is good if you really understand at least how some of them are working or how the process goes behind the scenes. But I think that looking at some of these plots give you some more intuition about how you should choose. So that's why I didn't show that, but there's definitely some resources like that out there to help you make a very strong objective based decision on the number of clusters.
Thank you. That helps.
The next question is from Carlos Hernandez. So is there any criterion or threshold value to select characteristics from the length of each int vector in the PCA biplot?
I don't like my answer is I don't know. If anyone knows, please feel free to share your thoughts. I mean, of course, you want to see higher correlations, right, between higher eigen loadings or higher loadings on those eigenvectors, meaning that the variable has a very strong effect. But I actually have not really tried to play with that much, you know, because, yeah, I guess that would be the answer is really I don't know.
All right. Any other question? If we don't have another question, thank you, Leo, and thank you, everyone. We appreciate you being here, and be aware that a record version of this workshop will be available for you on the AGSA YouTube page. Thank you again, and we will see you tomorrow at 4 p.m.
Awesome. Thanks, everybody. Carlos, can you
Yes.
wait just a little?
Yes.
I just, because if you close now, I don't get to read the messages and I
Okay.
cannot go back to them. So I just want to take a look at them because I didn't during the workshop.
We'll just stop recording.